Here's problem 3021. Two long parallel wires each carry a current of 5 amps directed to the east. The two wires are separated by 8 centimeters. What is the magnitude of the magnetic field at a point that is 5 centimeters from each of the wires? If this point is 5 centimeters from each of the wires, it's not going to be in the same plane as the two wires themselves. So let's draw this with the two wires, two currents coming out of the page towards you. So here's our x-axis, and we have current here, I1, coming out of the page, and I2 also coming out of the page. That means they each would be 4 centimeters away from the origin, since they're 8 centimeters apart. And if we have a point P that is 5 centimeters from each of the wires, then we have ourselves a 3, 4, 5 triangle to point P. So this side will have to be 3 right there. Imagine that the internal angle here is theta. And in a 3, 4, 5 triangle, that theta should be about 53.1 degrees. So this total angle here at point P is actually 106 degrees. So it's not going to be a right triangle, a right angle. The complementary angle to theta is alpha. And so these will be alpha up here, because we're part of a right triangle there for these smaller right triangle like this. Alright, the magnetic field due to each of these wires will be the same because we have the same currents and the same distances. And that's going to be equal to mu naught I over 2 pi r for an infinitely long wire. Mu naught is 4 pi times 10 to the minus 7. The current is 5 amps over 2 pi, and then they're 5 centimeters away. 5 times 10 to the minus 2 meters. 4 pi divided by 2 pi is going to leave a 2. The 5's cancel out. 10 to the minus 7 divided by 10 to the minus 2 is going to be 10 to the minus 5. So this is 2 times 10 to the minus 5 Tesla. That's the same magnitude for each. And if we were to look at point P, we would have a magnetic field, B1. B1 would go off at a right angle like this, at a 90-degree angle there, and so let's write it down here as well. And then B2 would go off at a 90-degree angle like this. Using the right-hand rule for these two wires, these magnetic fields are going counterclockwise around the wires. So here's B2. They have equal magnitudes, and we're evaluating them from point P on the x-axis. Now as we look at this, we have a theta, and then we have another angle, which is the complementary angle to theta, which is actually alpha. So this angle right here is alpha, and that should be alpha. And if we look at the supplementary situation along the x-axis, we have a theta, 9 degrees, and then the last angle will also have to be alpha, because it should add up to a total of 180 degrees in a supplementary sense. So that angle is also alpha. Good to know. As we look at these same magnitude vectors, our x components should cancel out. B1x is the same magnitude as B2x, but they're in opposite directions. So our net magnitude in the x direction will be 0. Our net magnitude in the y direction will not be 0. We have a B1y and a B2y. Both of them the same magnitude, but going in the same direction. So they will add, and we'll have a net magnetic field in our y direction like this. That magnetic field, By, is then going to be equal to 2b sine alpha because of these two components in the y direction. That's going to be 2 times b, 2 times 10 to the minus 5. Sine of alpha. Alpha is part of this original right triangle here. And the sine of alpha is the opposite side over the hypotenuse. That's going to be 3 divided by 5, 3/5 for the sine of alpha. So we're going to have 4 times 3, 12 divided by 5, which is 2.4. So this is going to be 2.4 times 10 to the minus 5 Tesla. And that is our net magnetic field at point P going in a up direction in the y direction, which would actually be north. If east is out of the page, that would be in a north direction. And that would be our magnetic field. Or we could write it as 24 microtesla if you wish. So there's our net magnetic field.